Hey again, everyone. All right, let's look at solving trigonometric equations. This is textbook section 5.5, and we're going to look first at equations in linear form, and then equations involving arguments with multiple angles, arguments with compound angles, and then nonlinear trigonometric equations. So let's first just remember a little bit about linear equations. If we have 5x minus 3 equals 2x plus 1, notice that every x has no exponent, no x is in a denominator, so this is each x has actually the exponent of 1. This is a linear equation, and the goal is always to get x and the constants on opposite sides of the equal sign. Well, so in this case, I could subtract 2x from both sides. That would give me 5x minus 2x, and we still have minus 3 equals 2x minus 2x plus 1. 5x minus 2x is 3x minus 3 equals 1. And then we can add 3 to get the constant terms on the opposite side of the x terms. So we get 3x equals 4, and then we can divide by the coefficient of 3 or of x, or we can multiply by the reciprocal of the coefficient of x. And that's kind of how we're going to think of it, multiplying by 1 over the number. Well, 3 times 1 over 3 is 1, so on the left side here we get x, on the right side we get 4/3, and we would normally need to check that equation. We're not going to do that now. Let's look at trigonometric equations where every trig function has the first exponent. So the first thing, we want to isolate the trig term on one side of the equal sign and the constant term on the opposite side. So just like we did with x. And then we're going to solve for the trig function over the interval 0 to 2 pi. We're going to add 2n pi. You can think of 2n pi where n is an integer. N is an integer. And remember, the integers are like -5, -4, -3, -2, -1, 0, 1, 2, 3, 4, 5, ... So we're saying that if n is any integer, and I have a solution for a trig equation, I can add 2 pi, or if n is 0, I can add 0. If n is 5, I could add 10 pi. Any even multiple of 2 pi I can add, because that's like a coterminal angle. Okay, great. Let's see the kinds of steps we're going to need to use to solve this equation. First of all, I really want the same function on both sides. And I know that 1 over the secant of x is equal to, yes, that's right, cosine x. So I can rewrite this equation as 2 cosine x plus the square root of 3 over 2 equals cosine x. Now that I have all of the trig functions are the same function, I want to get the trig functions on one side excuse me, of the equal sign, and everything else on the opposite side of the equal sign. Okay, well, so let's subtract cosine x from both sides. 2 cosine x minus 1 cosine x is 1 cosine x. And we still have plus square root of 3 over 2. On the other side of the equal sign, we have 0. Now I want to move this constant term, square root of 3 over 2, to the opposite side of the equal sign from the trig function. So now I get cosine of x is equal to negative square root of 3 over 2. Oh, that's nice. So I've solved the equation for the trig function. I got it by itself. Now I want to solve this function between 0 and 2 pi. So where between 0 and 2 pi is the cosine equal to negative square root of 3 over 2? Well, here's part of the unit circle. And I can see that the cosine of 5 pi over 6 is negative square root of 3 over 2. So I know cosine is negative in quadrant 2. Where else is cosine negative? Very good. So here, x can equal 5 pi over 6, or x can equal 7 pi over 6. These are the two angles in the quadrants where the cosine is negative that have an x coordinate of negative square root of 3 over 2. So we've done the first part. We've solved for the trig function over the interval 0 to 2 pi. To get the next step, I want to notice that x equals 5 pi over 6 plus 2 pi is also a solution. X equals 5 pi over 6 minus 4 pi. That's also a solution because I'm going right around the unit circle. I'm landing on the same place. These will be coterminal angles. And the way that I can summarize this idea is by adding x is equal to 5 pi over 6 plus n times 2 pi, where n is an integer. This is a z with a double bar. We use the letter z because in German, integer starts with z, and that's where the word was developed. Okay, so I want to write this as one fraction. I really don't want to have two parts. So let's see, I can write this as n times 2 pi over 1. So that means I need to multiply by 6 over 6. And I get 5 pi over 6 plus, and now I'm going to put the n in here and put 12 n pi over 6. So I moved the n, I switched the n into 2 basically. The pi stayed. And now I can write this as one fraction. 5 pi plus 12 n pi all divided by 6. So for every single integer, I can plug in an integer here for n, and that will also be a solution. But we had another solution. So our other solution, 7 pi over 6 plus 2 n pi over 1, again times 6 over 6. That's 7 pi over 6 plus 12 n pi over 6, and we get 7 pi plus 12 n pi all over 6. it's nice to write the final answer in set notation. So let's look at set notation. I can say x is equal to x bar x equals. Just a moment, let me see what that is. Okay, yes, it was one of y'all. So set builder notation says all the x's, so this is all x's, and this line is the words such that okay, sorry about that. That was one of y'all. So all the x's such that x is equal to whatever. So here's how we want to write this solution. We want to write it as x is equal to, with set notation you always use braces, this curly kind of thing, and I put the variable, this variable in the front says this is what I'm talking about. I'm talking about x, and I'm talking about all the x's such that x is equal to 5 pi plus 12n pi over 6, or x is equal to 7 pi plus 12n pi over 6. Close. Oh, where n is an integer. And here's what it looks like pretty. All of the x's, and then the bar represents the words such that, and then we have x equals 5 pi plus 12n pi over 6, or x equals 7 pi plus 12n pi over 6, where n is an integer. Go ahead and pause the recording and work this problem out. There's a hint that you could possibly replace the cosecant here with its reciprocal. So I want you to solve for x. First over the interval 0 to 2 pi, and then over all real numbers. So go ahead and pause the recording and do that problem, and then start the recording back. Great. Well, here's another fun one. I've got 3 times the tangent of x plus 1 equals negative 2 times the quantity 2 plus the tangent of x. And again, I want to solve it first between 0 and 2 pi, and then over all the real numbers. So the first thing I need to do is get rid of these parentheses. And to do that, I need to multiply through by that negative 2. So I get 3 tangent x plus 1 is equal to negative 4. Let's see, negative 2 times positive tangent x will be negative 2 tangent x. Now that I have no parentheses, and nothing in a denominator, and I have the same trig function. I want to move the trig functions to one side of the equal sign and the constant terms to the opposite side of the equal sign. It doesn't matter which side I choose, I just have to choose a side. I don't know why, but I like it to be on the left, so that's what I usually do. So we're going to add 2 tangent x to both sides. That eliminates the tangent term on the right, and we get 5 times the tangent of x on the left. We still have that plus 1, and on the right we still have minus 4. Now I want to move all the constant terms to the opposite side of wherever I put the trig function. So that means I'm moving the constant terms to the right, and I have 5 tangent x equals negative 5. And I can simplify this by multiplying both sides by the reciprocal of 5. So instead of thinking of it as dividing by 5, I'm multiplying by 1 over 5. It's the same end result, but multiplying is loads easier than dividing. Well, here we have 5 over 5, those cancel. Here we have negative 5 over 5, that's negative 1. So we get tangent x equals negative 1. So let's think. On the unit circle, first of all, where is the tangent function negative? Which quadrants? That's right. Quadrants 2 and 4. So I need to look in quadrant 2, first of all, and see where is the tangent negative 1. But I know that tangent is sine over cosine, and as long as the sine and the cosine have the same value, but opposite plus or minus signs, then I'm going to get a tangent of negative 1. So 3 pi over 4 is the quadrant 2 value. And 7 pi over 4 is the quadrant 4 value. These are the solutions over the interval 0 to 2 pi. To extend this, to get the general solutions over all the reals, we're going to add, this time we're not adding 2n pi, we're adding n pi, because the period of tangent is just pi. It repeats every pi cycles. So I'm going to add n pi. And again, I want to get a common denominator. Let's do this one on the right first. We've got 7 pi over 4 plus 4n pi over 4. And we get 7 pi plus 4n pi all over 4. That's the general solution that came from the specific solution, x equals 7 pi over 4. Let's do the same thing with the 3 pi over 4. So we've got 4n pi over 4, and that equals 3 pi plus 4n pi all over 4. We can write that solution in a pretty way. Oh, there's something I forgot. So, okay, that's really good. I'm glad that I checked the notes. So let's check something out. If n equals 0, here. Then x equals 3 pi plus 4 times 0 pi all over 4. That'll just be 3 pi over 4. If n is 1, then we have x is equal to 3 pi plus 4 times 1 times pi all over 4. And let's see, 3 pi plus 4 pi is 7 pi over 4. But check this out. That was our other specific value. So with tangent and cotangent, you don't need to list both values on the unit circle when you list the general solution. So in this case, our general solution is going to be all of the x's. So this first part says all x's. The bar is the words such that. Let's see. All of the x's such that, and then we have x equals 3 pi plus 4n pi all over 4, where n is an integer. I want y'all to pause the video, please, and do this example 4. Okay. Now let's look at solving equations. These are still going to be linear equations, but where the argument is a multiple angle. So, argument, what? So here, let's just remember what an argument is. If we have f of x equals whatever, this thing that's plugged in is the argument. It's what we're plugging in. Well, with sines and cosines and trig functions, we'll have the sine of, let's see, 4x. This would be a multiple angle as an argument. We're plugging in not x, but a number times x. And this r with the double bar is all real numbers. So here the steps are, we want to isolate the trig function on one side of the equal sign. We want to find all the solutions to the equation, assuming that a is 1. Whatever this constant is, we're going to assume it's 1. Then we're going to write the general solutions and set each of them equal to a times x. We're going to let the actual value come back, and we're going to solve for x. And then we want to substitute values of n into the solutions and find which values are within the desired interval. And most of the time, the desired interval is 0 to 2 pi. Great. All right. Well, we've got sine of negative 3x is equal to square root of 3 over 2. And I don't want that negative in there, but I remember that sine is odd, which means that the sine of negative x is negative sine x. So I can rewrite the sine of negative 3x and pull that negative out front. This is equal to negative times sine of 3x, and that equals the square root of 3 over 2. But this has to get the trig term by itself, not negative the trig term, but the trig term. So I want to multiply both sides by -1 so that I have a positive sign on the left. So -1 times negative sine 3x is positive sine 3x. Square root of 3 over 2 times -1 is negative square root of 3 over 2. Okay, so we've done the first step. Find all solutions assuming that a is 1. Well, let's see. Sine of x is equal to negative square root of 3 over 2. So let's just look at this. 3x would be, it's not 2 pi over 3, 4 pi over 3, and 3x is 5 pi over 3. So we needed quadrants where sine is negative. Sine is negative in quadrants 3 and 4. And I know that sine of something with a denominator of 3 in lowest terms is going to give me square root of 3 over 2, and I wanted negative, so I chose two angles where sine is negative. So that was this step. Now we want to get x alone. So I'm going to multiply both sides of these equations by 1/3. If I divided by 3, I would have 4 pi over 3 divided by 3. And that takes several steps. Doing it this way, on the left we have 1 over 3 times 3x. The 3's divide out. On the right we have 4 pi over 3 times 1 over 3. We multiply the 4 pi times the 1 and get 4 pi. We multiply 3 times 3 and get 9. So I have x is equal to 4 pi, oh, excuse me. Okay, the miracle of the recording. It paused and I was able to fix something. So before I multiply both sides of this equation by 1 over 3, I need to add plus 2n pi. So I'm going to put plus 2n pi, and I'm going to put over 1. And the same thing here. Plus 2n pi over 1. Because I want to divide both numbers by 3, or multiply both numbers by 1 over 3. So again, I'm multiplying every term by 1 over 3 to cancel the 3 in front of the x. So on the left I have x equals, and now I've got 4 pi over 9, 3 times 3, plus 2n pi over 3, but I need to add those, so I'm going to multiply this second term by 3 over 3. I get 4 pi over 9 plus 6n pi over 9, and now I can write them together. 4 pi plus 6n pi all over 9. And what's nice about this is that I don't have to redo the work on my second equation. Because 2n pi over 1 is going to be this exact same term. So here I've got x is equal to 5 pi over 9. If we multiply everything by 1 over 3, plus 6n pi over 9, and we get 5 pi plus 6n pi all over 9. Now, what we want to do, we've got two really nice solutions. X is equal to 5 pi plus 6 times n times pi over 9, and x is equal to 4 pi times 6 times n times pi over 9. But I want to list the solutions, and I want to list the solutions that are between 0 and 2 pi. So let's do that. First, we're going to let n equal 0. So the equation is going to be x equals 4 pi plus 6 times 0 times pi over 9, and that's 4 pi over 9. And I'm going to do the same thing over on the second part. X is equal to 5 pi plus 6 times 0 times pi over 9, and that's 5 pi over 9. Those are our first two solutions. Now let's let n be 1. So I get x is equal to 4 pi plus 6 times 1 times pi over 9. And let's see, we've got 4 pi plus 6 pi, that's 10 pi over 9. For the other value, we get x is equal to 5 pi plus 6 times 1 times pi over 9. 5 plus 6 is 11, so we get 11 pi over 9. Let's let n equal 2. So now we've got x is equal to 4 pi plus 6 times 2 times pi over 9. Let's see, 6 times 2 is 12. 12 plus 4 is 16 pi over 9. And then we have x is equal to 5 pi plus 6 times 2 times pi over 9, and that's 12 plus 5 is 17 pi over 9. How many values do I need to keep looking for if I only want answers that are between 0 and 2 pi? Well, let's check it out. We've got denominators of 9 all the way. So I want to see 2 pi over 1 times 9 over 9. This will give me something equivalent to 2 pi, but with a denominator of 9. 9 times 2 is 18. So I can go up to 18 pi over 9, but no bigger. And I'm already at 17 pi over 9, so I do not need to do 3 pi, letting n be 3. And now let's write our solutions. X is equal to this is the most enjoyable part, nonlinear trigonometric equations. So in general, when you have something that is not linear, the goal, the first goal, is to get all terms on the same side of the equal sign. because we're going to use something called the zero product property. And that says if I have two things that are multiplied and they equal 0, one of these things must be 0. There's no other way to get 0 as a product unless one of the values that we're multiplying is 0. So this means either A equals 0 or B equals 0. We're going to use this property to find solutions for these non-linear trig functions. And the first one is pretty non-standard, but it's just too much fun not to do. So let's look at the steps. We want to get all the trig functions having the same trig function, move all terms to the same side of the equal sign, use substitution to simplify the equation by replacing the trig function with u, solve for u, and substitute back for the trig function for u. Okay. But I've got a cosine and a sine. I don't know how to make them look like each other. So there's a trick. Of squaring both sides. When you square both sides of an equation to get to a solution, let's write this down. When you square both sides of an equation in the process of solving it, you may get extra, and the correct word is extraneous, solutions. So you must check answers. Anytime you square both sides of an equation in the process of solving the equation, you must check your solutions, because you may have an extraneous or extra solution. Okay, so we've got some cool stuff. Now, how do I square sine x minus 1? Well, I'm going to use a minus b squared. I know that's a squared minus 2 times a times b plus b squared. Okay, that's not so bad. So sine x is a and 1 is b. So I'm going to have sine squared x minus 2 times 1 times sine x plus b squared, so plus 1 squared. That's all on the left, and the right is just cosine x squared, which we write as cosine squared x. Well, this is wonderful because I do know how to replace cosine squared x with something involving sine. So I'm going to use that wonderful Pythagorean identity. I'm going to use the version cosine squared x is equal to 1 minus sine squared x. So I've got sine squared x minus 2 sine x plus 1 equals 1 minus sine squared x. I've finally done the first part. All the trig functions are the same function. We have only signs. Now I need everything on the same side of the equal sign. So let's move everything to the left. That means we're going to subtract 1 and add sine squared x. Okay, so we're going to have 2 sine squared x minus 2 sine x, and the positive 1 minus 1 is 0, equals 0. Okay, I've got everything on the same side. We've got all terms on the same side. Now I'm going to use substitution to replace the trig function with the variable u. So here we go. I'm going to let u equal sine x. And the reason we do this is that it makes it so much easier to see what kind of equation we're solving. So I've got 2 sine squared x, that's just u squared, minus 2 sine x is u, so u equals 0. Can I divide or multiply everything by 1/2? Because that will certainly simplify the left-hand side. 0 times 1/2 is still 0. 1/2 times 2 is 1, so I get a u squared, minus 2 times 1/2 is also 1. So I have u squared minus u equals 0. Let's factor this, because we have a common factor of u. U times u minus 1 equals 0. And now I have the product of two things. The product of two things is 0. That means, so by the 0 product property, either u equals 0 or u minus 1 equals 0. I can solve the second one for u by adding 1. I get u equals 1, u equals 0. So here are my two solutions for u. And I'm only looking at 0 to 2 pi. Now, did I want u? No, I want sine x. So now that we have our solutions for u, let's see, what step was that? So we solved the new equation for u. Now we're going to replace u with the sine of x. So I have u equals 0 becomes sine x equals 0. U equals 1 becomes sine x equals 1. On the interval 0 to 2 pi, what angles have a sine of 0? Well, exactly right. We know that x can be 0 because the sine of 0 is 0, and x can be pi because the sine of pi is 0. 2 pi is too big because we're not going all the way to 2 pi. Now what about 1? What value of x has a sine x of 1? Exactly right, the top of the unit circle. So here, x is equal to pi over 2. But remember I said we have to check. So let's see. We've got solutions x equals 0, x equals pi over 2, and x equals pi. And we want to substitute these values into the original equation. We have to do that because we squared both sides in order to solve it. And that can create extraneous roots or solutions, extra solutions. Let's see. On the left, we have sine x minus 1. On the right, we have cosine x. And let's plug in our values for x. We have 0, pi over 2, and pi. So let's see, the sine of 0, sine 0 minus 1. The sine of 0 is 0. 0 minus 1 is just negative 1. The cosine of 0 is 1. So these are not the same. Cool. Now we've got the sine of pi over 2 minus 1. And I know that the sine of pi over 2 is 1. 1 minus 1 is 0. The cosine of pi over 2, well, that's 0. Cool, so this agrees. So pi over 2 is a good solution. And the sine of pi minus 1, the sine of pi is 0. 0 minus 1 is negative 1. Cosine of pi is negative 1. It works. So our two solutions, one of them did not pan out. Our two solutions are pi over 2 and pi. Oh, I'm doing another one. I forgot. Okay, great. So now let's look at this equation. The cosine x plus 2 equals 3 secant x. And let me pull those steps back up here. I want all of the trig functions to be the same. But this is kind of nice because I know that secant x is 1 over the cosine of x. Okay, so we get cosine of x plus 2 equals 3 over cosine x. But I don't want fractions. It just makes everything harder. So I'm going to multiply every term by this denominator, by cosine of x. On the left, I've got cosine x times cosine x. That's cosine squared x. And I've got 2 times cosine x, so plus 2 cosine x equals, on the right, the cosine x is divided out, and we just have 3. And now I can do this next step. I can move all terms to the same side of the equal sign. So I'm going to subtract 3 from both sides. And now we've got cosine squared x plus 2 cosine x minus 3 equals 0. Now that I have the same trig function throughout and everything on the same side, I'm going to replace the trig function with the variable u. All right, so we're going to let u equal the cosine of x. So now we've got u squared plus 2u minus 3 equals 0. Well, that's a quadratic. I know how to solve quadratics. I just need to factor. Let's see. What times what is negative 3 that adds up to positive 2? Let's see. The ways that I can get 3 as a product, and let's see, when I want negative 3 as a product and 2 as a sum. So let's see, 3 times negative 1. If I add those, I get positive 2. So this is what I want. So I've got u plus 3 and u minus 1. Now I have the zero product rule. I've got the product of two things equals 0. The zero product property says that either u plus 3 equals 0 or u minus 1 equals 0. To solve the first equation for u, we're going to subtract 3 from both sides, and we get u is equal to negative 3. To solve the second equation for u, we'll add 1 to both sides, and we get u is equal to 1. We're doing it. Let's see. We solved for u. Now we're going to substitute u with the trig function. So what was u? U was the cosine of x. So I've got cosine of x equals negative 3, or cosine of x equals 1. What's the very largest that the cosine function can get to? Yes, 1. And what is the smallest that the cosine can get to? That's right, negative 1. We know that the cosine function is stuck between the values negative 1 and 1. That means the cosine of no angle will ever be negative 3. So there's no solution for this first equation. Well, what angle on the interval 0 to 2 pi has a cosine of 1? Well, that's easy. I know that the cosine of 0 is 1, so our only solution here is the angle 0. Oh, this one is kind of nice. So the first thing I'm going to do is move everything to the same side, because I don't know what else to do. So I get, let's see, negative 3 cotangent x minus 3 cotangent x. So I've got cotangent x times tangent squared x minus 3 cotangent x equals 0. Well, that's good. Now, I do see that I have a common factor. I've got a cotangent x in both terms. So let's factor out that cotangent of x. In the first term, tangent squared x is left. And in the second term, the negative 3 is left. And look what we have, a zero product property. So that means that either the cotangent of x is 0 or tangent squared x minus 3 is 0. Well, cotangent, where is cotangent equal to 0 on the interval 0 to 2 pi? I know that cotangent is going to be 0 whenever the cosine is 0, and cosine is 0 at pi over 2 and at 3 pi over 2. So here I'm going to get x is equal to pi over 2, or x is equal to 3 pi over 2. So that equation is done. Now, this was a linear equation. The second equation is not, because we have a square. So here, I'm going to use the u substitution. I'm going to let u be the tangent of x. And I'm going to rewrite this equation. So it'll be u squared minus 3 equals 0. I want to solve for u. Let's add 3 to both sides. So I have u squared equals 3. To get to u, I need to take the square root. But I'm taking the square root of both sides of an equation, so I need a plus or minus. Square root of u squared is u. So u is equal to plus or minus the square root of 3. But now let's back substitute. Let's replace u with tangent x. So tangent x equals plus or minus the square root of 3. Well, where is the tangent positive square root of 3? Let's see. The tangent is positive square root of 3 at pi over 3, and it is negative square root of 3 at negative pi over 3, or at 2 pi over 3. So let's see. Tangent is positive in quadrants 1 and 3. So tangent x equals positive square root of 3 has solutions. It's all going to be over 3, so it'll be pi over 3. And in quadrant 3, it'll be 4 pi over 3. And then tangent x is negative in quadrants 2 and 4. So tangent x equals negative square root of 3 has solutions 2 pi over 3 and 5 pi over 3. And now we have lots of solutions. I mean, we have lots of solutions. So x is equal to, it's kind of fun to try to put them in order. And the two solutions that we had from the cotangent equation were pi over 2 and 3 pi over 2. It looks like pi over 3 comes first. Pi over 2 comes next. 2 pi over 3 comes next. 3 pi over 2 is larger than 4 pi over 3, so 4 pi over 3 comes next. Then 3 pi over 2, then 5 pi over 3. Let's see, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Yay! All right. The rest of the problems are y'all's to do. And I cheated this time, and I put them on the same page. So here are examples 12 and 13. Solve the equation sine squared x minus 2 sine x plus 1 equals 0. And solve the equation sine x minus 6 equals negative 5 cosecant x. And both of these solve over the interval 0 to 2 pi. Just pause the video while you're copying those down. And have a great day.